you all for showing up here. And since it's my first live talk post-pandemic, I'm going to get it. Everybody smile. If you don't want your picture on social media, turn around and always smile. Okay. I don't know if it'll be on social media. So anyway, thank you for being here. This talk is about taking the leap from microcontrollers to FPGAs. And does everybody know what an FPGA here is here? Okay, so I think most of us are familiar with them these days. They're out a lot more in the press, a lot more people are writing about them, talking about them. They're some pretty easy to use, easy to get started with products. There are products out there, two of them right here that I'm familiar with. The pictures of a tiny FPGA and one big square with their icebreaker. Great little barriers to entry. But what happens, or what happened to me, is I was a microcontroller expert. I spent years and years and years programming, C assembly mostly, and some other languages. And then I was convinced to take the leap to FPGAs, and I thought that's really cool. I started looking at the language. Syntax is very familiar. The arrangement of the files is very familiar. But there are some things that I discovered that coming from the microcontroller world actually caused problems. And so I made some terrible, terrible mistakes. And I was doing this publicly. I was writing a column about this as I learned FPGAs. So I would write about something, it's a great discovery I made about how these wonderful tools work. And I put up a code sample. And then down in the comments, all of these FPGA experts from around the world would go, Duane, let me tell you something. So, you know, it was a fun process there, and you know, I don't mind making mistakes because really it's all about what you do after you make a mistake, how you recover from it. But there were a lot of frustrations there. And so that's what this talk is all about. You're used to programming, you're familiar with programming, and you want to start using an FPGA. So what are you going to trip over? Now, this is not a comprehensive course. You're going to have to learn about, you know, a lot of things in other places as well. But what this is going to do is outline some of the most significant traps that you'll run into. And so you remember this, or you can download this PowerPoint from my website. And as you go through this journey, hopefully this will be a little bridge over some of these little tiny chasms that you'll run across. So first of all, why in the world would you want to use an FPGA other than the fact that they're cool and they're different? Well, you're creating hardware in an FPGA. So you are designing and developing essentially a chip, a custom ASIC. But it's a custom ASIC that you can change every single time you power it on. And that's you know, a marvelous thing if you use a lot of digital logic, or you need to use a lot of digital logic. And then one of the other things that I find is really cool, excuse me, sir, could you raise your hand? Take it back down. Raise your hand. Take it back down. Raise your hand. Take it back down. So that's the software world. Everybody raise your hand simultaneously. Take it back down. So however many people, that's parallel processing. That's something you do with FPGAs, or you can do with FPGAs. And in this particular illustration here, I was working on a robot, and I had all of these little microcontroller boards that control motors or sensors or whatever. And I wanted to feed them into a main microcontroller. And then scan through all of it. Well, if it's a mobile robot, your speed is dependent upon how fast the motors can go, but also how fast you can see what's going on around you, do the sensor fusion, and then take your next move. If you've got to scan around all these sensors, that takes time. With an FPGA, I can create as many different I2C interfaces in that FPGA as I have pins for, and as I have fabric inside of the FPGA, and run them all parallel. Parallel processing easy. So what I found is it is a mysterious world, but it's not as big a jump as I thought. There are now FPGA development boards that are $100 or less. And, you know, if you're in the corporate world, well, you don't have to worry about that so much, but if you're a hobbyist or in an unfunded startup, a maker, that's pretty important. So, tiny FPGA, 1-bit squared, Papilio, there's quite a number of these things. You can just Google inexpensive FPGAs. And a lot of different options. So let's look at what's the same what's pretty much the same as a microcontroller and what's different. So they use an IDE. How many of you program in IDEs? How many primarily program with the command line? Okay, you can program these things with a command line also. IDE is most common. You got multiple files in the development set, that's very familiar. You've got multiple language options, although not as many. You'll hear the term Verilog. That's the one that I use the most. It's one of the more popular languages for FPGAs. VHDL is another one that's one of the more popular ones. MyHDL is an open source based on Pascal. There's System, Verilog. There are people who program them in C and a few other things. Primarily Verilog and VHDL. But there are more and more software tool sets opening up for these things. So you have some flexibility, not as much as microcontrollers. So you code and then you implement. And then the syntax is often pretty familiar, although that can be a problem, as I'll show you. Not the same. You don't turn it on and go. Most FPGAs, you've got a ROM, and you've got the FPGA, which is empty, sitting there brainless. You power it up. It loads the bit file, that's what we call it, once it's crunched down, bit file. Loads it into the FPGA, turns that into an ASIC, and then you're ready to go. And that can be pretty quick, or it can take, 20, 30, 90 seconds, maybe even longer. So you're instant on like you get with a microcontroller, don't expect that. The FPGA isn't running code, so you're not running your program. Unless, of course, you can actually create a CPU inside of the FPGA. Then you have your code that will be running on that CPU along with all of your custom hardware. You are literally creating an ASIC that is then a piece of hardware. And you have to wire up the chip pins to the innards. Some microcontrollers these days have crossbars where you can change where a peripheral sits. Every single pin, or almost every single pin on an FPGA is that way. You have to assign it before you can do anything with it. You've got your brains, you've got a crossbar all over the place, and you can tell where that signal is going to go. Okay, so what do you need to get started? Digital logic knowledge is really, really handy. Although you can learn digital logic as you're going. But most folks in the computer industry have some level of, you know what an AND gate is, or an AND function. That's really, really handy. You'll need to know that at some point, but you can learn it as you go. AND gates, flip-flops, common terminology within the digital hardware world. Familiarity with IDEs or comfort level with command line programming, either one. And then, as I said, microcontroller programming experience is helpful. It will both help and hurt. And probably programming microcontrollers is more relevant than if you're an applications programmer. So development environments, all of the major brands have them. There are some open source development tool chains coming out. It's a tool chain that's like you've used your entire career. Okay, so you've got it, and now what do you do with them? And this is where, again, this is not a detailed tutorial. Remember that. These are the traps, but I'm going to walk you through the order that you go here. So the first thing you need to do is define what they call constraints. And that basically is things like, okay, pin number 1. What goes to pin number 1? Is it an input? Is it output? What voltage is it using? Things like clocks coming in, You define all of those things in what's called a user configuration file, user configuration file, logical preference file, lattice preference file, a couple of different names, but if you hear UCF, LPF, what you're doing is you're connecting pins to something inside and you're defining the operating parameters, voltages, timing, things of that sort. Then you code, you write code, that's pretty familiar. Then you simulate. In most cases with an FPGA, you want to simulate your design before you crunch it because it can take an awful long time to synthesize it, synthesize it into the code that's going to work in your FPGA. Hours, sometimes days to do this. So most of the good, well, all of the big commercial tool chains have a simulator. And that is exactly what it says. It's simulating your design, showing you the timing. You can give it inputs and outputs, and you see if it's going to work or not, and hopefully catch all of the major traps there, the major bugs there. Then you synthesize it, you crunch it to the final bit file, and then that is what gets loaded onto your FPGA into the non-volatile RAM, and then a power up goes from that non-volatile RAM into the FPGA. You've got the three primary file types, and again, this is not absolute, this is more abstract. There may be other types, but in general, you've got the UCF or LPF defining the pins, port locations, timing parameters. You've got your main code, and then you've got modules. And that's actually pretty familiar. You know, if a program, you might pick microcontrollers. I've got setting all the bits, the configuration bits. I've got my code, I've got my modules. Again, very familiar there. So here is a UCF file. And I'll go do this. So there's a lot of stuff in there that may or may not look familiar and probably is meaningless if you haven't used one of these things before. In the blue, those are labels that I have created. They're not reserved words. It's like a variable name. There are rules for them, but basically I'm creating those names. The physical chip pins, BGA, so it's a big BGA that this one was referring to, so it's got A through at least V, and then down 20 pins or something down. So those are the pin numbers. I'm defining, so I've got a clock coming in. I've called it clock 66 megahertz because it's a 66 megahertz clock, very original. And net, that is essentially a wire. I'm connecting that wire to pin K15, and it is a 3.3 volt CMOS signal. So you can see all this information in there that would be defined in your microcontroller by the people who laid out the silicon. It's here in this. Now let's look at one individual line down here. So this is a button, reset button. I called it user reset, again, very original there. So it's on pin V4, 3.3 volts, and I've got a pull-down resistor. Your microcontrollers, typically you can add a pull-down or a pull-up resistor either in the configuration or on the board. You can do that here in the UCF file. So now on my board, so that's the board there. That pin is labeled SW4. There's a couple of different here, couple different pins or switches, and I could pick any of those to be my reset if I wanted. So now in step 2, the physical board, the PC board, you can see that's, well, you might be able to see, that goes from the switch to pin V4, and over here, pin V4, I'm calling it user reset. So now I have taken a random switch, I've connected it to the FPGA, and I've given it a name that I will now use inside of my code. So let's go ahead and, technical difficulties. So let's look at the Verilog code file, which is the main file. This is like your .c file, or for whatever language you're using.
So you break it up into a couple different parts here. The modules and modules and ports, you see up there clock 66 megahertz, user reset, LED. Those are connected to these labels here, which again to the physical ports. So this is telling my Verilog code what it is that I'm going to be doing. So I'm calling those inputs wires, outputs wires. A wire is really a wire. Some people will refer them to nets wires, but we're telling them it's a wire. And I start it with the parentheses and end it with an end parenthesis and a semicolon. That's familiar syntax. Next, I've got some more wires here, and those are declarations. So those wires aren't going to the outside world. They are wires going from one part of my FPGA to another. Now you see this assign. Assign is something different. I'm going to talk about that a little bit later. But what that's doing is making sure a signal or a register or value is always available at the clock enable. So I'll go into that more detail there later. The BFGCE, that is calling an external module. So like in your C code, you call a library function. That's doing that, except here, you're not calling that function at runtime. What you're doing is you're telling the system that I want to build a clock. So over here is a template of a clock. I'm going to build that clock when I power this thing on and load the bit file into the FPGA. So that's what that's doing there. Register, I'm defining a place to put the LED counter. And 26 through 0, so I'm reserving 27 spots for that LED counter. It's not really an array. It is a set of bits, a register, and that's where I'm going to be storing that data. Now we've got clocked circuitry. So some things in an FPGA happen with each clock step. You know, do this, do this, do this, do this. Do this, do this, do this, do this. Other things are like an AND gate. You know, you've got your little proto board, you put an AND gate down, you put two ones in there, and instantly there's a one on the outside. Well, instantly minus the propagation delay. That's called, that's called, I'm sorry. I lost my terminology here. That's combinatorial logic. Excuse me about that. Combinational logic. So an assign means whatever is in LED count, it's always going to be available on that wire up there. So that always happens. That happens instantly. The always is like a looping function. Feel free to ask questions, by the way, as we're going along here. So now let's put some of these things together. Kind of the three major things you're going to be dealing with: wires, assigns, and registers. And a wire, again, a wire is just, you can't really see them, but a wire is just a physical wire. And the reason this terminology is so important is because when you're going from the microcontroller world, you've got C equals B, A equals 23, A equals some function. You don't really think about these things. A register is your storage. You can have something going from a register to another register. You've got to wire it up. And you've got to have that wire going through the, to your output pin. You can read wires, but if a wire doesn't hook to a register, there's nothing there or it's unpredictable. One of the first traps that I ran into was I had some wires going directly into some of my code, and the results were just weird. Somebody says, "Did you register it?" And I'm thinking, what? Do I have to call Microsoft and register a DLL or something, call it a DMV? No, it simply means you have a register sitting there that you're going to put that data in. So the wire is for reading what's in a register. The wire isn't for processing. I was trying to process on a wire. And if you have a ribbon cable sitting someplace and you try and do processing on it, it doesn't work. Works about as well as an FPGA. So that's why wires and registers are really important. The assign is basically making a permanent connection. So I've got the wires and the registers, and I put values in the registers. When I power up the FPGA, assign is going to say, this wire here, a wire, that's my term, is equal to whatever value it sees in a register or a wire. So that's always there from the very moment. And you can receive something on a wire. Let's see, what do I have here? I better drink water. So my middle comment there, an assign cannot be used within an always block, because the assign means to wire something up at configuration time, where the always block is our triggered module. So you can't assign something in a triggered module, it just always has to be there. Another thing that tripped me up is this here is in my UCF. You notice we saw the net commands, or the net declaration, the LEDs. Again, I was treating that like an array when I first started, thinking, okay, well, you've got LED 0, LED 1, LED 2. It's like an array. It's not. Again, this particular case, when it's called a net or a wire, it's more like a ribbon cable. You're transmitting information. So, net is just another term for wire. You use them in different places. So, like in that particular case, net means I've got several of them together, a ribbon cable, where wire you can use as an individual one. So output wire, that I'm calling LED, now what I had to do is I had to create a register. Again, the register is that's where you store the data. It's like a memory cell, kind of like a memory cell, not exactly, but that's where you're storing the data. The wire connects between it. If you look at the little tiny loop there, the always and end, that's like your main loop or a main loop in a C program. So I'm counting in there, but I've got my assign outside of that. So I'm doing the counting inside. The assign is outside of the loop. It's always reading what's inside that loop. And this is what I was getting at before, clocked versus combinational. So clocked, like a flip-flop, again, you're doing something clock-based. Combinatorial, combinational, it's like a digital logic chip. You put something on the input, it's there on the output, minus a little clock propagation delay. So here, again, out of all of this, this is the clocked circuitry. So when you've got clocked circuitry, so you can do it in two different ways. You can have more of these always blocks. And I'm going to tell you something dangerous about side 2 in a minute here. But with C, you pretty much have one main, and it calls everything else. In your Verilog file, in your hardware description language file, Verilog, VHD, or whatever, you can have more of those main loops. So here in this particular case, I'm flashing 3 different LEDs independently. They're all on the same clock, but I'm not doing this in sequence. That's all happening exactly at the same time, like the hand raising, even though these are different main loops. You can do that with one clock. You can do that with different clocks also. Again, there's some dangers with this, but if you have to have a 66 megahertz loop and then a 100 megahertz loop, you can do that inside of an FPGA, provided you have the clocks available in your FPGA. So you can do things differently like that. Again, danger when you're matching those, connecting those two things up, but you can do that. And that's something you can't do in a microcontroller. So combinatorial, so that was the clock logic. Assign is the key. So from my prior Verilog code, assign clock enable equals user reset. None of that other stuff has to run. None of that other, I don't have to have my clock running because it's outside of the always block. I don't have to do anything. The minute that bit file is crunched into my FPGA, that assign on the top and these two on the bottom are in place, and they will always be in place until I power the thing off. So you can get yourself into trouble that way too, because if you're depending on something to happen in sequence, because I've put it in an order there, it's not going to work that way because they always happen. So down on the bottom there, gate out Y equals gate in A and gate in B. That's a simple AND gate. And that's combinatorial logic in its most basic form. So here calls it out in a comparison to the microcontroller world. So your while there, that's the loop that's going on. I'm doing essentially the same thing, except anything outside of the while loop, while one, my port A.0 equals flash value, nothing happens. All the math is still going on, all the logic is still going on, but it's not connected to the outside world. In the FPGA world, in the red box is roughly equivalent to what's there in the red box. My assign is outside of that loop. And from an MCU world, you might think, oh, it doesn't happen. But it does, because that assign happens at power up, and when the bit file is loaded in. So it's really important to remember that some of these things, if you're used to the order mattering, if it's an assign, in general, the order does not matter. And this illustrates that again. So this is our hand raising at the very beginning. In the MCU world, you're calling a function, it finishes. You call another one, it finishes. You call another one, it finishes. These ones there, those three things are happening at exactly the same time. Right. So the full bit file is read in at power up, and then you have a piece of logic ready to go, and hopefully you have something in there to make it start whatever you're doing. Inputs coming in are being read, a clock is being...
Can I ask a clarification on that? I think earlier on you mentioned that can take a while compared to
Yeah. Seconds, tens of seconds, sometimes longer for a really, really large FPGA. So registering, and I mentioned this a little bit earlier, but I wanted to give this a specific slide because this caused me a lot of trouble. I was trying to do processing on wires. I was trying to do math and have the result end up on a ribbon cable. And the experts were asking me, well, did you register that? Or a wire coming in. I was looking to do math on a wire when data might vary in the wire, and I'm assuming it's going to stay the same. So they were using the term registering. Again, it confused me. It simply means define a register and put the wire into that register, and then do your math, do your reading based on that register from a wire. And I wanted to call one thing out. It is noon right now, so if anybody's like getting really antsy, I won't be offended if you get up and run to eat or anything, but so we're running a little over time here. I hope that's okay. Mm. Mm-hmm. Mhm.
Yeah, I think we can have a slide for say, these are the kind of reasons why.
Yeah, that's a very good point. And some things, microcontrollers are not going to go away. CPUs and MCUs, TPUs are not going to go away. They have very important uses, and there are things you can do with them. Like if you need instant on, you've got to have a microcontroller. But say you're doing video processing and you need to process large chunks of data in parallel, that quadrant, that quadrant, that quadrant, or this layer, this layer, this layer. Each one of these always blocks potentially is processing a layer or a quadrant or a massive set of data. And, you can get your big CPUs involved in that and, burn up tons and tons of power, or you can do those things in parallel. So you can do things that involve massive amounts of data that need to be done in parallel. Yes, you could, almost anything you can do with an FPGA, you can do with a CPU or an MPU also. However, things like that are really well suited to this, or say you happen to be, your end product is on Mars. The Mars Perseverance rover has something like, I think it's 20 or more FPGAs in it. And if there's a problem in the hardware, you can send it new hardware, basically. So you can upgrade the hardware in place in a very remote area. And that's why one of the reasons why they chose to do that there. All of that parallel processing, all of the sensor fusion, with multiple cores, yes, you can do a pretty decent job of sensor fusion or with really high speeds. But there are times where you really need to look at things all at the same time. So if you're bringing in a bunch of sensors, you send that into combinatorial logic, and it's just there. You're welcome. So earlier on, I'll skip over this because we're running out of time because this is pretty important. But earlier on when I talked about you could do the same things on multiple different clocks, well, what happens sometimes if you're not careful is when you're doing things based on two different clocks, the clock edges don't line up. And so you try and trigger something before a transition from a 1 to a 0 is fully completed. So it's sort of like Schrodinger's logic. You don't know if it's really a 1 or a 0, or maybe it's both, or sometimes it's one or another. This is a really easy trap because the lure of multiple clocks is really enticing at times. Like I said, what if you want to do something on a 66 and a 100, or you've got something that's internally clocked, and you've got something coming in that comes from a different clock, but it's asynchronous, so you have to determine the clock. It's really easy to enter a condition called metastability, which is when the FPGA, that particular logic gate, can't tell what's going on. It can't tell whether it's a 1 or a 0. And what you need to do is you have multiple flip-flops from one clock domain, so that gives it time to settle down. Again, metastability, remember that term when you're fiddling with these things. Spend a little time researching it because it's something that if you're not careful, it can really cause a lot of issues. Libraries and modules look very similar to the software world again. Very simple example, an AND gate. So I created a library function that was an AND gate, and then I called it multiple times. So you can see I've got inputs, 2 inputs, and an output, A, B, and Y, just like any other AND gate. Down in the bottom is the assign. That's actually the logic. That little ampersand is the AND function.
I have a question about that. So with creating this, you're able to use a basic syntactic thing to make it in?
Yes.
But if you're creating something more complicated, you'd have to build it up from syntactic blocks that exist.
Yeah, if you have multiple AND gates, you're going to have multiple layers of syntax, but you can have that particular symbol will be used throughout. And there are different symbols for different functions. Then there are also, there's some flip-flops that you can bring in. So it's a little bit different than the language you're using in C to do this, complex logic. But for combinatorial logic, that's the most simple form, and then you build it up from that. Okay, and this is what's really, one thing that's really, really important. Again, a function, you're reusing code. So I was the code when I was asking you to raise your hand, reusing me to say, raise your hand, lower your hand, raise your hand, lower your hand. In an FPGA, you're not doing that. Each of these, we call it instantiate. You're creating a flip-flop in hardware. So that had called the same module, but it's a template. So when I power up that FPGA, I am creating the 3 different flip-flops, and they can be anywhere in the code that the synthesizer decides they need to be, or anywhere in the chip. So not calling, not reusing code. I'm creating logic from a template. Okay. So that was a lot to throw into half an hour. What I hope is you've heard some terms that will really, really help you when you start this journey. It hopefully will have dropped a little bit of the mystery, and that when you want to do this, you're going to go ahead and find yourself a little development board, a tiny FPGA maybe. I understand they were giving those out yesterday. Something like that, and just give it a shot. You can download this on my blog, download this presentation on my blog, and go through these different things and just trigger. Each of these are really research jump-off points. So each slide I've got here, there's some basic information to help you, and those are areas you want to study when you're taking your own FPGA journey. And, there's 1,000 times more than this. This is such a tiny little touch on the surface.
Can you recommend an IDE that's good for beginners? Because I've tried using Xilinx stuff, and that kind of suffers from the engineering problem where it's a really powerful tool that exposes everything all at once, so it's completely overwhelming.
I had a lot easier time with the Lattice tool set, and we all have our preferences, but I found Lattice to be a lot easier than the Xilinx tool set. I mean, at some point, I couldn't even install the Xilinx tool set properly. It just was getting so complex and so in depth, and they're adding in all of their ARM programming functionality with this. So I'd take a look at something like the tiny FPGA. It uses a Lattice, they call it the ICE chip, and I'd start there.
So you go from FPGA
Their FPGAs tend to be more expensive, but some of them, like this ICE series from Lattice, are comparable to a mid-range MCU. You can buy a development board for a few tens of dollars for one of these things. Crowd Supply has a couple of them, and they're showing up in other places as well. So for less than $100, you can get yourself a pretty powerful FPGA. For probably $30, you can get something that gives you a really good solid education, and you can use in your hobby or maker projects. You can use in real world applications. That's going to be, I'm not going to be able to give you the most accurate information because I've never designed an ASIC. But I would say the big thing is, looking back in my history to one-time programmable parts or, UV erasable proms. You design it and you program it, and well, there you go. So you have to have an awful lot more discipline, especially in the simulation phase with hardware, an awful lot more discipline, because with an FPGA, I mean, it can take a long time to crunch it, but then you can redo it. You don't have 100,000 units out in the field that you now have to recall. Mhm. Mhm. Yeah,
That's something that you can integrate into FPGA really easily.
yeah,
You don't have to buy another chip to do that.
yeah,
Maybe even have, an SoC where you have a microcontroller and FPGA on the same board.
yeah. That's an excellent example. You can create a coprocessor of sorts. I mean, you can create a literal, central processing unit in an FPGA, or you can create a logic-based coprocessor. Specialized math, for example. You might have something that just does these complex vector analysis. CPU's off doing all of its stuff, running the device, and your FPGA is taking that complex, real specialized processing and handling that.
Maybe you can do simulation for synthesis for the performance. Is the synthesis deterministic enough that that's safe to not have to say for design interact with the synthesis where you want to simulate that?
Theoretically, the synthesis is close enough that you can synthesize and then run and have good confidence, but then you also have to test and verify. So you've got a verification. I mean, if it's not the real thing, it's not exact, but these days they're pretty darn close. Anything else? Well, thank you all so much.